Okay, so now the recording has started. I'm chairing this session from Trento. We will have two speakers this morning. We will start now with the first one, who is Gurtej Kanwar, who will tell us about flow-based generative models for ensemble generation. Thank you, Tej.
All right, hopefully my slides are visible. Let me just make this full screen. And perfect. Okay, thanks so much. So firstly, thank you to the organizers. I very much appreciate your work in putting together this first hybrid conference after many delays and so on. And thanks to everyone who's both joining in person and virtually. So today I'll be speaking a bit about this recent work that I've done during my PhD with what is now quite a large collaboration of folks across institutions in using these flow-based models to generate lattice ensembles, so collections of lattice samples from well-defined distributions that one can then use for physics. And so while I am now at the University of Bern, this was done under the funding of IFI and MIT while I was a PhD student.
Sorry, Tej, can we change the view perhaps so that?
Yes, should I click on one of these?
Part of your,
Centro or no?
No, it's just the view on the Zoom.
I see.
So we go Campodio. Okay, so that now your slides are visible.
Good.
Okay, thank you.
Okay, thank you. Right, so I've left a list of references. I'm sure this is too small to read, but in case anyone's curious, in the slides posted afterwards, you can take a look. So firstly, let me just thank a large group of collaborators across institutions, MIT, DeepMind, Heidelberg, and NYU. And as I have now graduated my PhD and sort of moved on, these folks are going to be carrying the torch forward. So I'd encourage you, if you find anything interesting here, to go chat with any of them and hear more about what the future directions are going to be. But for today, let me just start off by giving a quick 30-second lattice primer. I'm sure most in the audience are already very familiar with this, but this just establishes some notation. So I'll generally be talking about the lattice discretization of field theory, which with a focus on gauge theories. So in that particular realm, we typically think of the discretization of the gauge field in the Wilsonian approach as consisting of these discretized link variables, u sub mu of x is the notation I'll use. And these take group values, which for example could be SU3, so 3×3 complex matrices that are unitary and determinant 1. And then the matter fields are discretized typically to live on the sites of the lattice. So the idea is that this discretization gives a well-defined meaning to a well-defined regularization to what is otherwise an ill-defined QFT path integral, and therefore a well-defined regulated meaning to observables that one would like to compute. And of course, there are some caveats, namely that typically to actually do these calculations numerically, one goes over to Euclidean spacetime. So sampling is possible for this distribution e to the minus s. And ideally, one would like to remove these lattice artifacts when we're talking about quantum field theories and tune towards a second order critical point where the lattice spacing is essentially effectively shrunk to 0, as all correlation lengths are infinitely longer than that lattice spacing. So the main motivation for this talk is based on actually generating these ensembles and effectively measuring these observables, which is standardly done with Monte Carlo, as I'm sure everyone's familiar with. So the idea being that this lattice regularized integral, which eventually by some extrapolation of a to 0 gives rise to continuum observable values, can for a given lattice regularization be approximated using Monte Carlo sampling in terms of these sampled configurations drawn from just what is this normalized distribution over configurations. And one can clearly see taking this ensemble average gives an expectation, the observable that you want, and you can extract controlled errors essentially on such quantities by standard statistical methods. But to do the sampling of these gauge fields is typically done with Markov chain Monte Carlo. So iterative updates to an existing configuration, typically by some sort of perturbative, not perturbation theory, but small perturbative updates to the field. And the idea being this asymptotically converges to P, of course, and so that after a sufficient amount of thermalization time and skipping sufficiently many configurations to avoid correlations, you can build an ensemble on which to measure. But the main motivation, the motivating problem, of course, is that as this lattice spacing is taken to 0 in a lattice field theory calculation, the autocorrelation time tends to diverge for these sorts of local or diffusive Markov chains. And that can sort of be understood physically in that the correlation length on the lattice is growing in lattice units. And so it takes many more local updates to mix information at a given physical length scale. And there's also this effect of topological freezing whenever you have some sort of topology, because it's rare that you would update the entire field coherently and jump between topological sectors. And so this has been well studied in, say, Lattice QCD, but it also affects a number of other models, whether lattice field theory or statistical lattice models. So this is a significant obstacle to the continuum limit and therefore to extracting physical information. So we should find ways to work around this problem. So what I'll be talking about is one particular idea to circumvent critical slowing down or to mitigate it. It doesn't necessarily have to be fully solved, but as much as you can do to the problem to reduce computational cost. And this idea comes from this picture that really drawing lattice samples can be related analogously to an image generation problem in some sense, in that there are typical looking lattice configurations with fluctuations at the right length scales that should be much more likely than the bulk of the possible configuration space. So most configurations just look like noise, which can be likened to just a noisy picture with no meaningful information. But then there's this small subset of configurations that are typical. And in the image generation case, maybe you're interested in typical images that, for example, represent human faces. And that's a small manifold that you'd like to sample from. But there are distinctions, and that sort of motivates our choice of flow-based models, as I'll describe in just a second. So the caveats here are that for lattice sampling, of course, we'd like to maintain the systematic control. So eventually you can pull out a physical observable with well-defined error bars. So ideally, you should know something about the distribution that your model is sampling from so that you can then make this sampling or an estimation problem exact. There's also, this tends to be the case in some of the more recent image generation approaches as well, but there's a big issue of an inverted data hierarchy, which has been mentioned in previous talks, in fact, in that within each configuration you have, it's at the state of the art, say 10 to the 9 or 10 to the 10 degrees of freedom, but typically you'd only have something like 10 to the 3 samples from a particular set of Baire parameters. So you can't actually do this brute force training approach of throw a large amount of data at a problem to learn the distribution. But instead, we do have these advantages that this target probability density is just known analytically. So if I give you a configuration U, you could plug it in, compute e to the minus action over z. And also we know things about symmetries of the distribution. So my focus will sort of bend towards integrating these symmetries in, and also how flows take advantage in particular of knowing the density. So these advantages are really why we've chosen flow-based models, also known as normalizing flows, because sort of in contrast to image generation with something like a GAN, where you don't know what distribution you're sampling, flow-based techniques, which have also been applied to image generation, give you samples, but they also give you the probability distribution. So you can, given a particular sample, you can measure what the probability density was to draw that sample from the model. And so this is useful when you'd like this exactness to be built into your sampling procedure. And it's also useful in terms of training because one can compare that density against the analytically known density. So the remainder of the talk is sort of split into 3 broad parts. Because we had sort of touched upon in this workshop the idea of baking symmetries into these generative models, as well as the phase classification models, I thought it would be interesting to kind of bend the focus towards symmetries and how they're baked into these models. So I'll briefly start by introducing flow-based generative models, but then the main bulk of this talk is going to be talking about, well, how can we bake symmetries into those? Can we learn anything sort of general that goes beyond flow-based models in terms of symmetries in lattice theories. So let me just start then by giving this brief overview of what flow-based generative models actually are in contrast to any other generative approach. So the idea is to start with typically convolutional neural networks, but generally neural nets, and build this well-defined sampling model around what is otherwise black box function approximators. The idea being that these generic function approximators can be put inside a coupling layer. And what a coupling layer does is it takes your field configuration, it applies some invertible transformation to it, and it's constructed such that the Jacobian of that transformation is tractable, so that one can measure what one knows that it's an invertible transformation of the configuration space. And if you can measure the Jacobian, you can measure the squishing and stretching of the density. Whatever probability density you had over configurations to start with will be squished and stretched by this transformation in a measurable way. And so I'll delve into this example in a second. This is just to give an overview, but the idea being that you've placed your black box component in a precise way such that this construction is possible in a flow-based model. And then those coupling layers essentially can just be composed end to end. If I have one invertible transformation, I could just put any of them in sequence, and that together is an invertible transformation. And if I measure the Jacobian of all of these, I can multiply that together, and you have this change of variables formula that essentially tells you end to end, how did I change my probability density? So I start with something that's simple to sample, say a Gaussian distribution. I apply a bunch of these coupling layers, and then I get an output density that's a function of all of these coupling layers, and in particular is a function of what the neural net parameters are inside each of those. So those could be optimized ideally to make this output probability density agree with the target that you'd like. The training then is based on this Kullback-Leibler divergence, which I'll mention in just a second. And you can use standard procedures to optimize all of these neural net weights inside each coupling layer. And this does enable exactness because one can take the measured density of any samples that you draw and just apply corrective factors to say reweighting, for example, is the simplest one that comes to mind to account for any bias between your target distribution and what you're actually sampling from the model. So let me just delve deeply then into how we construct these flow functions in our particular coupling layer based approach. So the idea is that this flow function end to end, which is giving you some invertible transformation of your field configuration, as I said earlier, must be an invertible function with a tractable Jacobian determinant. And that's necessary because you'd like to, let me just move this box out of the way, you'd like to plug in the Jacobian into this change of variables formula for the probability density. So assuming that these properties are satisfied, you will have some model that you can sample from and that you can measure the density of. But of course, for lattice quantum field theories, we typically don't know what that function has to be in order to make this output agree with the target, to make the output essentially look like e to the minus action divided by some normalization. But the idea being that we're working with machine learning here, so instead we can just come up with this parameterized ansatz. And the parameterization is really by decomposing the flow into this composition of coupling layers and placing a well-parameterized neural network kind of parameterization of each coupling layer in each of these steps that one can then optimize. So yeah.
So you start with, say, a Gaussian distribution initially, and then you want to end up with something that looks like e to the minus s. So you could also start with something that has already been generated from e to the minus s, and then improve it somehow.
Yeah, so I said Gaussian just as an example of something you can sample from and measure, but you could, for example, use an ensemble from a different action. That's perfectly valid.
Okay, cheers.
Yeah. Of course, we would like to typically have a lot of training data, and so it's nice to have something you can generate many, many samples from. So probably you want an easy to sample from action as your starting point. Okay, so moving on to this composition of coupling layers, I just want to give a brief sketch of what each coupling layer is typically constructed as. And the structure of this is kind of important as to how symmetries are then baked into each coupling layer. So the idea behind a coupling layer is simply to take your lattice configuration and split it into two subsets. One is going to be, one subset will be transformed, and the other subset will be held fixed. And the transformed subset is updated only as a function of the fixed degrees of freedom. And the result of this is that you get this explicitly upper triangular Jacobian structure, so that the Jacobian determinant is efficiently calculable simply from the diagonal elements. And you know, for example, that the transformation is invertible because all these diagonal elements of the updated degrees of freedom, you can just ensure that each of those transformations is invertible, so the elements are not zero. Just to make that all concrete, so that's a very abstract picture of coupling layers, but it's useful to actually look at an example in the simplest lattice theory that one can apply these flows to, namely real scalar field theory, where you have one real degree of freedom per site, and a simple coupling layer, which actually comes from the image generation community, known as a real non-volume preserving coupling layer, or real NVP, could be applied to transform these scalar fields. The way it works is simply to do a checkerboard decomposition, which I think feels very natural from the lattice perspective. So you'll take, say, the even sites and make them be frozen, and the odd sites and have those be the updated degrees of freedom. And the way the actual update works is to take the frozen degrees of freedom, you plug it into some neural net, and you get out some parameters, one scaling factor and one offset factor per site that will be updated. And so this defines an affine transformation element-wise per updated site. So you do a scaling and you do an offset of each of those degrees of freedom. And that's a manifestly invertible transformation as long as you have these parameters, which you can always recover from the output because they're only computed from untransformed degrees of freedom. And a key point here being that this neural net defining those parameters can be arbitrarily expressive, arbitrarily non-invertible, and you still get these guarantees that you would like, that this is an invertible operation regardless, and that the Jacobian can be computed by looking at these scaling factors and multiplying those together. But, you know, this is just some generic construction. We'd like to put some physics intuition into it. And so the next sort of consideration is, okay, you've generically constructed coupling layers, but let's say I want to put translational symmetry into one of these scalar fields generating generative models. Can we make any, in a sort of brute force and generic way, can we make any flow model symmetric under the translations, regardless of what parameters I put into my neural nets? And the answer turns out to be yes, if you do these precise constructions in terms of invariance and equivariance. So let me just detail what I mean by that. If you take an invariant prior distribution, so I start with something that is already translationally symmetric, say an independent Gaussian per site, that's a translationally symmetric distribution, and I compose it with a flow that's equivariant under the symmetry operation. So what that means is this flow function, if I translate the input, the output will translate correspondingly. So if I put those two together and I define my flow-based generative model using this pairing, then the model is guaranteed to be symmetric. This is not the only way, it's not an if and only if, but this is sufficient to guarantee a symmetric model, and it has kind of a natural interpretation also of what the coupling layers are doing. They all have well-defined then transformations of the fields that respect the symmetries independently. And so this is kind of a nice intuitive construction that tends to work well in practice. And the motivation for working with symmetries, of course, as mentioned, is that we know that they exist in the target distribution. So one would like to restrict your variational space to things that satisfy the symmetries already. That's just a smaller space. You might have less data complexity of training, fewer model parameters potentially required to define your model. And it, for example, may make the loss landscape easier to search through because you have, you just essentially restricted the space that you walk through, and everything will be translationally symmetric or symmetric under whatever symmetry you're considering. So in the case of translations, there's actually a very easy way to impose this equivariance. So I won't really talk too much about invariance because typically it's easy to pick a prior distribution that's invariant under these symmetries, but the equivariance of the flow function is the more interesting thing in the context of flows. So translational equivariance can be straightforwardly enforced using convolutional neural nets inside these coupling layers. So the idea being, for example, for this scalar field coupling layer, if I just restrict this neural net to be a convolutional neural net in particular, then these output values, the scalings and the offsets per site, are defined to be local functions of the frozen degrees of freedom. And they're also, the outputs are equivariant. So if I translated my frozen degrees of freedom, the parameters e to the s and t would translate. So I can imagine that if I translate my input, then both the frozen and updated degrees of freedom will correspondingly translate, and the output will also translate. So this then is equivariant to translations. Input translation equals output translation.
Tej, I have a question myself. Are these scaling and translation unique once you have defined a field? And does it matter in case?
These parameters,
yes, parameters.
Yeah, so it is fixed once you've defined the frozen degrees of freedom, what the output will be. So this convolutional neural net has no randomness or anything built in. That's right.
Okay, thanks.
Yeah, so the question for those online was, is the scaling always positive by definition? And yeah, so the way I've written it here, it's e to some output of the convolutional neural net. So it will be a positive scaling factor. I could have replaced this with just s of x. And so then you can get positive or negative scalings. But it turns out that for stability reasons, I think people typically choose this e to the s. And that's what was done in the original real MVP paper as well. Okay, so I should also mention that, so I mentioned that convolutional neural nets will make this coupling layer equivariant to translations pretty much immediately. But what was sort of subtly buried in that, an assumption, is that the masking pattern itself should be invariant in some sense. So choosing this checkerboard means the translation of the masking pattern itself is invariant under even sets of translations. And so that's the remaining preserved symmetry group in this construction. Okay, so let me then wrap up this quick summary of how flow-based models are used for sampling. So I've mentioned the construction. You can say draw from the prior distribution, pass it through the flow, you get a sampled output. By measuring the Jacobian factors, you can always measure the probability density of this model. But of course, ideally, you'd like to now train that probability density to match the target distribution. And you want to do so in a way that doesn't require a large number of samples from the real distribution, because that's simply kind of tautological. You would have to already have drawn a lot of samples, and that's the problem you're trying to solve. But a convenient approach here that has been known for a while in similar approaches is that you can do self-training. So this is commonly used in certain ML disciplines. For example, in like game strategy, you would use the AI to train itself by investigating its own behavior. It's also been used in these self-learning Monte Carlo methods. But the idea is simply, rather than using real data from the target distribution, at every step of training, you draw samples from the model. And because the model also knows its own probability density, you can now compare. For every sample that I've drawn from the model, I have some Q of X, but I also know I want this to look like e to the minus action over Z, so I know what P of X is. And you can define then a KL divergence between essentially those two distributions. And I won't really reflect on the math here, but the point being, if I draw a number of samples from the model, I can construct an unbiased estimate of the KL divergence using this estimator involving just the model probability density and the action, both of which can be computed. I don't really want to reflect on how one exactly might go about making the samples from a model unbiased, but just to point out that even though at the end of the day, we're going to have only some approximation to the target distribution, because we know Q of phi as well as P of phi, or Q of the gauge field as well as P of the gauge field, bias correction can be done exactly using, for example, reweighting, or we've also investigated this MCMC scheme based on proposals from the ML model, which has a different autocorrelation time, typically shorter than the standard approaches like HMC. So just to pause then and take a quick bird's eye view, the idea of these flow-based generative models is that I can parameterize essentially some ansatz for a distribution of field configurations using these coupling layers and a prior distribution. Each coupling layer contains some neural net, and then I go and train the parameters in those neural nets using the self-training. And once that's reached some desired accuracy, you can save out the trained model, and later one can go and generate, for example, using this flow-based MCMC proposals or reweighting, you can generate an ensemble, and you can measure observables with bias corrected, so unbiased observable estimates. as a result of this model. Okay, so then that brings me to the second part of this talk, which is to dig into lattice gauge theories in particular, and how gauge symmetry and translational symmetry interact with one another. So as a reminder, the gauge field is discretized in terms of these link parallel transporters u mu of x, which take values in the gauge group. And typically, lattice gauge theories satisfy a number of symmetries, but those include translational symmetries, which we've already talked about, hypercubic symmetries usually as well as a gauge symmetry, which for anyone unfamiliar, the key point is that this looks like the transformation of each of the links by matrix multiplication from the left and from the right, according to a field of matrices, so one matrix per site. And for any choice of this field of matrices, that defines the symmetry transformation. And so all these symmetries are essentially factoring, as in this previous picture, the distribution into some uniform direction and some non-trivial kind of physical degrees of freedom. And the idea being, if we can enforce as many of these as possible, we'd like to restrict our ansatz to be only exploring distributions that already satisfy the symmetries, especially when the symmetry group is large. So you factor out a large number of dimensions in this space by doing so. But I'm going to focus on the interaction between gauge symmetries and translational symmetries, because it turns out it's kind of interesting how one might try to enforce both gauge and translational symmetries at the same time. And we have one particular approach, but I think this is still a space that could be explored further, especially in the context of non-flow-based models. Maybe there are other nice solutions that come up when you think about lattice gauge theories. So to start off with, one can start thinking, okay, well, my distribution factorizes into pure gauge directions and physical directions in terms of pure gauge degrees of freedom and physical degrees of freedom. So maybe one approach to making the distribution satisfy the symmetry is simply to factor out all the pure gauge degrees of freedom, or in other words, to gauge fix. One way to do so would be what I like to term explicit gauge fixing, where you actually find and remove explicit gauge degrees of freedom, and you're left with fewer link variables at the end of the day. So for example, one can do this maximal tree gauge fixing, where all the bolded links are set to the identity matrix by a specific choice of gauge transformation, which is fixed by this pattern. And then all the degrees of freedom that are left are physical degrees of freedom. But this explicit gauge fixing is somewhat at odds with translational symmetry and locality, in that, well, first of all, the tree pattern is immediately going to break your translational symmetry, since this isn't a symmetric pattern, at least not in all directions. But it also breaks locality in that, for example, the link degree of freedom highlighted here corresponds in the original configuration to the loop about the gray shaded region. And you can imagine the higher up you go in this config, the more degrees of freedom are included in each remaining kind of gauge fix, remaining degree of freedom, sorry, after gauge fixing. So this seems generally like an undesirable feature. All of your links have different amounts of physical content, and the translational symmetry is now going to be fully broken down. Of course, you could imagine that it's learned by the model, but we'd like to enforce both if possible. So another thought is, well, one can use these implicit gauge fixing schemes based on differential equation constraints. Like, for example, Landau gauge is fixed by minimizing this function. Coulomb gauge is fixed by minimizing a different function where you remove the temporal direction. And this does as well remove the gauge degrees of freedom, at least most of them. But the idea being, if I use one of these implicit schemes, which is, by the way, translationally symmetric, all of the links at different sites are treated equivalently here, it's unclear how you remain in this subspace when you do these invertible transformations. So if someone had a bright idea for a class of invertible transformations in the fixed subspace that retains translational symmetry, I think that would completely work in this picture. But it's unclear, because this is such an implicit constraint, how can we transform the gauge fixed links and avoid breaking the fact that we're in this minimizing configuration of within a gauge orbit.
Yeah, just one comment on my side on this. I mean, you know, there could be even more than that. Gribov horizon could probably enter the picture there, so it's not even clear if it is well defined. An approach that is well defined in principle, the one of gauge fixing.
Right. So then there's the worries about Gribov copies as well, for sure. Yeah, I agree. So there's additional complexities as well in this approach. Although we did think a good bit about this because it's quite tempting on the face of it. It is very physical in some sense. You know what this gauge fixing procedure is, and it's also immediately translationally symmetric, which is a nice feature. But neither of these obviously had solutions in our mind. So the approach that we ended up proposing is based on working just directly with the link representation. So keeping all the link degrees of freedom around, but then just carefully enforcing that in the flow function that it's equivariant. So a gauge transformation of the inputs results in a gauge transformation of the outputs. And if you do so, of course, you never need to factorize and remove the degrees of freedom because you've already enforced this equivariance and therefore invariance after you pair it with a gauge invariant prior. Now, again, I won't focus on gauge invariant priors. It's not difficult to construct these. So for example, what one would think of typically as a hot start or a uniform distribution over links is invariant under gauge transformations, as well as translations, as well as literally every other symmetry, since it's the uniform distribution. But the gauge equivariance is really the main kind of direction that requires some thought. And the approach that we took is based on doing sort of a temporary transformation to loops of links. So take products of links in a loop, invertibly transform those loops, and then find out what the transformation of links must be in order to satisfy that transformation of loops, or to produce that transformation of the loops. So I'll distinguish here between open Wilson loops, the one without a trace, which transforms by this matrix conjugation, and closed loops, which is gauge invariant. And the idea being one can construct these open loop variables and invertibly act upon them. And if you want to think about those frozen degrees of freedom that are going into your neural net for conditioning, those will always be the closed loops. So we'll use gauge invariant quantities to transform these well-defined loops, and eventually we'll solve for what needs to happen to the links to make this all work out. Now, one sort of technical slide, I apologize, this one's a bit dense, but just to substantiate that a tiny bit, the way this construction ends up technically being made is we define two coupling layers, an inner layer and an outer layer that together does one invertible transformation of links. The idea is that you start with computing these field of Wilson loops. So in other words, this product of links, but translated to every possible base site. And the inner coupling layer is responsible for applying an invertible transformation to these matrix valued variables. And that could be done with any sort of standard looking coupling layer that, for example, we thought about already in the scalar field theory case, something where you do some masking and then you update some subset of the loops, the loop variables, sorry, as a function of the frozen loop variables. And again, just highlighting that when I say as a function of the frozen variables, I mean, make sure you take the trace first so that this is a gauge invariant function. These are all just caveats that make sure that the proof essentially goes through, that at the end of the day, you have a gauge equivariant coupling layer. And finally, the idea being that we would like to continue to work in the link basis because there's no one-to-one map between the Wilson loops and the links. And so the final step is to solve for some set of links, solve for the update of some set of links such that the loops transformed in the way that we wanted them to, or the way that the inner coupling layer prescribed that they should. So for example, for this sort of loop shape, if I propose a transformation from W to W prime, the idea being that I could choose to update just this highlighted link according to this value where V here is just the remaining black links. And then the loop would transform in the way that I wanted it to.
I mean, is it important to have different size loops, or can you just take your head?
So that actually was going to be my next slide.
Sorry, can you re-ask the question?
Oh, you will answer.
Yeah, I can also just say the question for those online. The question was, is it important to take different size loops, or can you work with just plaquettes here? And the idea is that you can actually just work with plaquettes. So for example, most of our experiments have been done with this passive active frozen pattern. And so the idea being these stripes of plaquettes are the variables that we're going to propose a transformation for. And that transformation can always be pushed onto the blank link, the bolded link here adjacent to each plaquette. And these transformations can be described as a function of the gray shaded traced plaquettes. Those are invariant and they aren't going to transform, importantly, after we push things onto the link. The minor caveat here, and that's sort of the purpose of this picture, is that we actually have to forget about these passively transforming plaquettes, which are ones that will update as a function of some other plaquette being transformed the way we wanted it to. This is a caveat that you can essentially forget about, but it's important to prove the gauge equivariance of these models. And then by composition of many of these plaquettes, plaquette-based transformations, you can expect to build in correlations at different length scales. This is sort of analogous to, for example, in the scalar field case, if I use a checkerboard and I use a very local convolution to describe the update, that's not really immediately building in long-range correlations, but composition of those layers could do so. Okay, so actually, I just want to jump back to highlight one point, which is that in the inner coupling layer, the transformation of the loops has to be done by what we termed a kernel. The idea just being that it has to satisfy equivariance under this matrix conjugation, which is how open loops transform under gauge transformations. And for U1, this is actually trivially satisfied. So this construction can immediately be applied in terms of any transformation of the loop variables because, well, the loops, no trace needs to be taken for U1, it's automatically gauge invariant. Although it was necessary to think a little bit, even in this regard, about how one should transform circular variables or variables on a compact periodic domain. I won't delve into that, but you can take a look at this paper. But then SUN requires some non-trivial engineering, essentially, of the mathematics to make this matrix conjugation transformation properties work out. I'm going to skip even the brief overview of how that works for the sake of time, but I'd be happy to go back if someone's curious to talk about it. But the point being that any equivariant function should work here, and then gives you gauge equivariance at the end of the day. So let me just skip those details and just briefly then flash some of the results that we got. So we tried this in this paper linked down below in U1 gauge theory in 2 dimensions, where there is a topological charge and there is topological freezing as you take, in terms of the Wilson gauge action, as you take the coupling parameter to 0, or in other words, the inverse coupling to infinity. And this is, for example, highlighted in this Markov chain history. It may not be super visible, but the idea being that standard methods like HMC or heat bath mix quite slowly on the order of tens of thousands of steps of Markov chain updates, whereas a trained flow-based sampler mixes the topology very, very rapidly. And so this allows precise estimation of topological quantities like the susceptibility with the flow-based methods in contrast to HMC or heat bath, especially at the larger values of beta. And this, if you go and then measure the autocorrelation time of the topological charge, there is, at the larger ends, many orders of magnitude gains to be made. And I should point out that each of the Markov chain steps for these methods was to within a factor of 2 the same computational cost in a single threaded implementation. So this is a real gain in computational cost, actually, at the end of the day. Same thing can be applied to SUN gauge theory. This is some particular construction that we used. We investigated both SU2 and SU3 as sort of the relevant lattice gauge theory groups, although there's no obstacle to going to higher SUN. Since there is no equivalent to U1 topological freezing to be kind of fighting with here, we just, instead of doing a full comparison across various methods, focused on confirming absolute model quality and the trainability of these models for SUN. And it turns out that one can indeed produce high quality models across a range of values of beta, including realistic looking values of beta from standard lattice QCD, say, calculations at lattice spacings you might be interested in. So what's listed in this table here is the effective sample size. 100% means that Q equals P. So the model is sampling exactly from the target distribution. And when there's some discrepancy, your number of effective samples from the target after reweighting is going to be smaller than 100%, but everything here is above roughly 50%. So you're doing no worse than 2x worse than directly sampling from the distribution itself. I'm also, again, for the sake of time, just going to skip over the details of the learned symmetries, although I'd be happy to go back to these plots, but we also investigated the spatial symmetries. Yeah, Biagio.
You have 5 minutes, just wanted to
thank you.
update on time.
Okay, so let me just say then that though this is in 2D, I would consider these promising early results because there's no theoretical obstacle in this gauge-equivariant construction to going to higher dimensions. In fact, we were chatting yesterday or day before about how there's practical obstructions, but we're working towards building the code and the infrastructure necessary to say run this in 4 dimensions. So of course, there's a lot more computational cost there. There's no well-implemented 4-dimensional convolutional kernels and so on. But once these are all tackled, essentially the same program can be run for 4D gauge theory. But let me then move on to what's still missing from this, which is the fermion content. So if we think about lattice QCD in particular, we'd like to include dynamical quarks, for example. And it's less clear, I would say, how fermions should be included, but I'll highlight some approaches we've thought about in these last 5 minutes. So fermions in field theory, as I imagine this audience is well familiar with, are represented by Grassmann numbers in the path integral. And integrating these out results in a determinant factor, giving you sort of a well-defined distribution still over gauge fields. But of course, computing the determinant factor is order volume cubed, and so is intractable at the standard scales of the state of the art. So often how standard MCMC is applied to this system is to integrate back in from the determinant pseudo-fermions, which are now ordinary numbers that can be sampled, distributed according to the pseudo-fermion action. Now, it's not clear what distribution one should even be trying to sample in a fermionic theory. So one of the first explorations here, as we investigated in this paper, was, well, which distribution really should one attempt to learn with a flow-based model? Should you attempt to learn the joint bosonic and pseudo-fermionic distribution? So that has an action of the form shown here. Should you learn just a marginal distribution where you keep this determinant around? And there's every other possible marginalization one could write down. You can combine these in a number of ways to produce samplers for what you eventually would like, which is samplers over just the field phi, here written generically. That's the boson field. Could, for example, in lattice QCD be your gauge configurations. So we essentially considered these 5 possibilities, and I'll talk in a second about a comparison of various possible ways one can sample these different distributions using different models. But a key obstacle in any approach that must sample pseudo-fermion fields is that they are defined to satisfy anti-periodic boundary conditions in the temporal direction on the lattice. And so this sort of throws a wrench in the works in terms of translational invariance. It's not a hard obstacle to solve, but there are several different ways one can imagine solving them. And that would be required for any model approximating a distribution involving pseudo-fermions. So just to lay out 3 example building blocks, we put out a few other options as well in this paper, but one could, for example, think about operating on a combined set of pseudo-fermions as well as boson fields using restricted CNNs. So the idea being that each channel satisfies a well-defined boundary condition in time, either anti-periodic or periodic. And it's clear how various operations involving these channels, what boundary conditions result for fields coming from various operations involving these channels. So for example, the multiplication of a field that's periodic in time with an anti-periodic field gives you an anti-periodic field back, and so on. So you can define several of these operations to combine channels in a well-defined way and never have something that's neither anti-periodic or periodic. It's always a well-defined output. And this allows you then to pull out parameters that are either definitely periodic or definitely anti-periodic and use those in coupling layers. Another approach could be to explicitly average over time translations with the appropriate boundary conditions. So you say my convolutional neural net output isn't going to be just the output of a single run through, but I'll look at all possible translations with the appropriate boundary conditions applied and take that and define that as my output. This is sort of brute force, especially as your time direction grows large, but it's very simple and easy to apply in many possible scenarios. And finally, sort of one that's a little bit specific to pseudo-fermions. So because they take the form of this Gaussian distribution, e to the minus pseudo-fermion, m inverse pseudo-fermion, you might think that, okay, well, you'd like to kind of produce them by a linear operation on Gaussian noise. So this is typically done even in HMC simulations, you start with Gaussian noise, you hit it with a linear operator, and you get pseudo-fermion samples out. But you also need to be able to compute the determinant for a flow. So we asked about restricted linear operators that one could use, where the action of the linear operator is straightforward, but also the determinant is efficient to calculate. And so one example is this restriction of linear operators where you only act in one direction on the lattice. Say you only pull in values from the plus X direction. And in doing so, you get a form that looks like one of these kind of circulant matrices, and the determinant is easy to compute in terms of the values on the diagonal and the subdiagonal. And so this is something that could, for example, be composed to make an arbitrary looking linear operator with enough composition. So that's a final kind of building block that we explored in this big comparison. So putting that all together, since it's unclear what the right really approach is here, we tried essentially a scattering of all of them covering these various building blocks. So things including sampling over the marginal distribution only, sampling both conditional distributions, so bosons conditioned on pseudo-fermions and vice versa in a chain, an autoregressive joint sampler where you sample to just the bosons and then conditioned on that you sample the pseudo-fermions to produce a joint sample, or as well as a fully joint model that produces both simultaneously. And I won't go into much detail here. The idea being we tried it in a Yukawa model with massless staggered fermions and found that everything trained to a level where the error bars were under control and in agreement with HMC. There were some minor differences in performance, but nothing that majorly made one of these methods stand out over another. And so I would say further exploration is required really to understand what would work well in a 4D gauge theory. So let me then just summarize by saying symmetries seem to be important to construct, at least in the flow-based case, efficient models. And in particular, we've looked so far at gauge symmetries and translational symmetries throughout in these various models. But I think that these symmetries are, of course, not only restricted to flow-based models. So I hope that some of these techniques might be interesting in other contexts. And I also think it'd be interesting to think about where other symmetries have been applied, can one import that into the flow-based sampling approach? So this leaves us with just a few directions, namely, we'd like to go to higher space-time dimensions and think about the scaling essentially of this approach. But that's all sort of work down the line for my collaborators to be thinking about as I slowly decouple from this, having graduated. But let me just end by pointing you to various other references. And thank you for your time, and I'd love to take any questions. Thanks.
So thank you, Tej, for the nice talk. I'd like now to open the floor for questions, starting from the audience in Trento. And colleagues on Zoom, please raise your hand. So let's start with Gert in the audience.
Yeah, just a very naive question in terms of, is there anything known how it scales when you go to higher dimensions? Because I guess a lot of the techniques are two-dimensional because a lot of machine learning is two-dimensional.
Right. So I would say there's two different things to worry about. One is the practical scaling in higher dimensions. As I said, there's no real good 4D convolution implementations right now and so on. That's all addressable, I think. I mean, you put in elbow grease and you can come up with nice code to do that. But the question could also be, do you get a different kind of scaling with number of degrees of freedom in higher dimensions, right? And in that case, I think it's not clear that the space-time dimensionality really should play a role. What I think does likely have some correlation with the scaling is, what is the correlation length? How does that scale as you approach the continuum limit? And we'd especially like to ask, for all of these methods, the question is, what gain in autocorrelation time do you get versus what increase in the cost of sampling do you have? So there's a trade-off there. And one would ideally like to draw a curve and say, as you approach the continuum limit, how does this trade-off scale? So that's something that we haven't yet addressed. I believe there was one paper out a few months ago. I want to say this was by Luigi Del Debbio and collaborators. And they started looking for, a particular class of flow-based models at the scaling and found that there's a pretty harsh training scaling. But I would point out that they also weren't using convolutional nets. So they had a version where they had a number of parameters that's order volume on the lattice, whereas convolutional nets, you just have a fixed number for any volume. So I think the scaling you should expect to actually be quite different, and it'd be quite interesting to repeat that study with one of these architectures that we've actually used.
I don't see questions on Zoom yet, so I'll move to Shrishit.
Thanks for the nice talk, Tej. And I have a question regarding, so do you see the dependence on, as you go from simpler systems to like gauge theories, the complexity of the CNN networks, how do they change? Like, do you have more number of neurons coming in? Or, you know, if do you see, so what I see at the end, you have only two layers, right? The S and T layers, the final.
Yeah, so to address the difference between, say, scalar theory and gauge theory, what we did in the scalar field theory, you did have only two output neurons, but there's of course all the hidden layers in between that one could scale. And in the gauge theory case, you again don't have that many output degrees of freedom. I didn't go into it for SUN, but you only have some order one number, let's say 5 or 6 for SU3 output channels. And so that scaling isn't harsh in terms of the number of output neurons that you need. But we did find that in gauge theory, it's helpful to increase the number of hidden channels in between. So I'm trying to remember off the top of my head, but I think in scalar field theory, we've made progress with things like in the range of 4 to 8 hidden channels in between in your convolutional nets. Whereas for gauge theories, it was helpful to go up to say 32 hidden channels inside. All of this, I think you should take with a grain of salt, because this is just one implementation. We did a scan in a few directions in terms of the model architectures and found what worked best. But I would say the fact that it's not going from 8 hidden channels to 1,000 hidden channels in the gauge theory case is already a good sign that you don't need that much complexity inside the convolutional nets. You're sort of getting the expressivity mostly from composition of these operations.
So thanks, Tej, for the great presentation. Just I missed something. What is the speed up for SU2 and SU3?
Yeah, so in fact, for SU2 and SU3, we never actually ran HMC results because there was no topological reason to compare with.
Okay, fine.
If I had to guess, I would say there isn't a good speed up in the SU2 and SU3 case. I think the evaluation time here would be some order one number between single-threaded HMC step and single-threaded SU2 and SU3 step. But HMC already mixes quite quickly, and these models are not bad. I mean, they have at worst the effective sample size is 50%, so 2 samples is roughly equivalent to 1 independent sample of the target. But if HMC is also 1 step roughly, or a few steps quickly mixes the distribution, then you'd expect that they have roughly similar autocorrelation times. You can see that I've listed the autocorrelation times as well here, by the way. And for flow-based models, it's 1 to 4 steps is autocorrelation time, but HMC is also 1 to 4 steps. It's quite a small number in mixing for these 2D pure gauge theories. So I would be mostly interested in checking that comparison in 4D gauge theory, where you start introducing topological charge.
Yeah, of course. Yeah.
Yeah.
Thanks.
Okay, back to Gert.
So you're keeping fit. Maybe you said it, but I mean, but for the fermion models, you also have this final exact step in it.
Yes.
I guess. And is that like is that the same as in Monte Carlo? It's cheap to compute. You don't need the full determinant or something like this.
Yes. Good question. So indeed, you need to worry about the fact that your reweighting factor, if you were to do it exactly, would involve a full determinant for some of these distributions. So if, for example, I think about phi marginal sampling, which I'm showing in this slide here, you would sample some bosons from just the marginal model, and you would have to do an accept reject step involving the determinants. So this would be expensive to scale, but other approaches don't have such a scaling challenge. So for example, if I sample a pair of phi and var phi, which is the pseudo-fermion, then the accept-reject step just involves the ratio of boson plus pseudo-fermion action to the density from the model. And so pseudo-fermion action, that's something you would do in HMC accept-reject step anyway. So this is approximately the cost of an HMC accept-reject step in points 3 and 4. I won't go into Gibbs sampling, but yeah. So it depends on which sampler you actually construct.
Cheers.
So there are no more questions in Trento. Are there questions on Zoom? So I can't see any question on Zoom. So one last chance. And Barak, could you please get ready? Okay, so we will move now to Barak Bringles. Thanks, guys.
Thank you.